Now that we know how to use gas laws, including the ideal gas law, we're going to get some practice using them in balanced equations. So when we are using the ideal gas law with stoichiometry problems, we're going to be doing the same process that we have been doing for all of the other stoichiometry problems we've been working on. So of course, our basic process started out taking us from grams to moles, and then to moles, and then to grams again, and we could start and end anywhere on that path. And then we added a second track where we could also use volume and molarity to get us from our volumes to moles. And now that we have added, or now that we have an additional tool, we have the ideal gas law that can get us to moles. So we have a new way to connect with our flow here, which is through the ideal gas law. And so that means that our starting properties are going to be some combination of pressure, volume, or temperature of our A. And we could theoretically go all the way to pressure, volume, temperature of B, but we may not. And we're going to use our ideal gas law to get in between these. And of course, this is our balanced equation. Okay, so a problem that we might work on might be a decomposition problem. So a compound called ammonium carbamate, it's not a normal kind of name that we are used to seeing. It's not carbonate, it's carbamate. And it has a compound formula NH2CO2 NH4. And it can decompose into carbon dioxide gas and ammonia gas. And so it goes straight from the solid form to the gaseous form. So let's say that in this scenario, we decompose, 18.45 grams of the ammonium carbamate. And we collect the ammonia gas, and we're going to collect it in an expandable container like a bag or something like that. And we're going to keep its pressure atmospheric pressure, so we're going to use 1 bar of pressure, and we'll just use room temperature, 298 Kelvin. So our question is, what would be the volume of the gas we collect? So let's think about our process here. Like any of our problems, we are going to do our process of identifying our A and B and identifying our start and our end. Okay, so the A is always the thing that we know about, and the B is the thing that we're going to ask about. So since we know what quantity of ammonium carbamate we have, that means that the ammonium carbamate is our A. And we are collecting the ammonia gas, and so that is our B. Now, we've done our first step, identifying A and B on our balanced equation. And now we want to figure out where we are starting and where we are ending. So we have information about the mass of the ammonium carbamate. And so that means that we are starting with grams of A, and then we want to figure out what the volume of the collected gas is. And so that's this right here. This is going to be our end. So this tells us what our path is. We're going to use our molecular weight to calculate moles of A, our balanced equation to convert that to moles of B, and the ideal gas law to calculate the volume. So let's go ahead and do that. we start with 18.45 grams of ammonium carbamate. And we need to convert that into moles, so we need the molecular weight. And when I calculated it, I calculated 78.0704 grams. And now I want to go to moles of ammonia. So I have 1 mole of ammonium carbamate. That produces 2 moles of ammonia gas. And anytime I am going to calculate something using the ideal gas law, I'm going to do a separate calculation. I'm not going to try and combine it into one step. So I'm going to calculate the moles of the ammonia, and then I'm going to use that number in the ideal gas law. So when I plug in these numbers to my calculator, I got 0.4727 moles of NH3. And now I want to use the ideal gas law. So my ideal gas law is PV equals nRT. I know I'm solving for the volume, so I'm going to go ahead and rearrange the equation accordingly. Oops, not V, P. I have, let's see what kind of information. I have my pressure in bar and my temperature in Kelvin. So I can go ahead and plug these numbers in. I have 0.4727 moles, and the gas constant I'm going to use is the one with bar and probably liters, because why not? 0.083145 liter bar per mole Kelvin. And then 298 Kelvin is my temperature. And the pressure is 1 bar. So when I plug that into my calculator, I get 11.7 liters, and I will only keep 3 significant digits because I only have 3 here on my temperature, and I only have 3 with my pressure. So let's think about this for just a moment here, and let's reconnect with some of the content that we just discussed. So in a previous video, I talked about standard temperature and pressure, and how 1 mole of gas takes up approximately 22.7 liters at standard temperature and pressure. Standard temperature and pressure was 1 bar and 0 degrees Kelvin, Celsius, which would be 273 Kelvin. So this is a little bit warmer than that temperature, and we have about half a bar. So notice that our liters, our volume is pretty close to half the volume here, and so that seems reasonable, especially since our temperature is a little higher than standard temperature and pressure. We won't always have a way to orient the numbers that we calculate with numbers, to kind of self-calibrate and make sure that they make sense. But anytime we're calculating a volume, we can do that. All right. So when we're doing stoichiometry problems with gases, we can ask about a gas's pressure, volume, temperature, or moles, or we can use that information to get the grams or the moles or the volume of a solid. So just going back to our little table here, this is what I'm talking about, right? We can start with any of these pieces of information. So we could have a gas and then be asking about volume, mass, or other gaseous information. And we can also just go from mass or volume and go to a gaseous product. So any of these kinds of quantities are ones that we can work with. So what I would do when I'm looking at solving these kinds of problems is to remember that my process is going to be the same. my process is going to be to first identify my A and B, and then I'm going to identify my start and my end, which we did that. And remember that we're going to follow the path using the tools that are available. And the tools that we have that are available to us are the balanced equation, any molecular weights for the compounds that we need, and in that case we might also use grams of a material. We might use molarities and volumes, and we might use pressure, volume, and temperature in order to get us to moles. So any of these tools are available to us. So let's go ahead and try another example and see how it goes. We'll see if we can do that with a little more independence this time. So one method of scrubbing or removing carbon dioxide from air or from any kind of a gaseous sample is to pass it through a strong base. And one of the best ones for that is lithium hydroxide. Lithium hydroxide is a strong base like sodium hydroxide, but what happens in lithium hydroxide is that the carbon dioxide will precipitate to make lithium carbonate. And lithium carbonate is a little less soluble than, I don't know, sodium carbonate, for example. And so it will precipitate out a little bit more effectively. You can still get sodium carbonate to precipitate out this way, but it's not as insoluble. Lithium carbonate is still not totally insoluble. It's just not very soluble. So on the solubility range, it still will dissolve a little bit, but it'll stay in solution. So this is a really effective way of sequestering carbon dioxide gas. And in fact, this has been used on spacecraft, like on some of the Apollo missions and stuff, to help keep the breathable air in the space station from getting contaminated by carbon dioxide. So let's say that if we have 5 liters of 2 molar lithium hydroxide, what volume of CO2 can be absorbed by the gas, or excuse me, can be absorbed from the gas, from air, if we keep it at 298 Kelvin and 1 bar of pressure? Okay, so let's review what we need. We have a balanced equation. This is one of our tools. We need to identify A and B, and we need to identify our start and our end. So we have a certain amount of lithium hydroxide. We're asking about carbon dioxide. So that means our lithium hydroxide is going to be our A, and our carbon dioxide is going to be our B. And for start and end, we have this information about the lithium hydroxide. So that means we're starting from our volume and our molarity track, and we are going to be going to our volume of gas track. So on our diagram, if I can get it to show up, there we go. In our new scenario here, we are starting here with volume and molarity of our lithium hydroxide, and we are going to end up with volume So here's our start, and here is our end. So we're going to use our molarity to calculate moles of lithium hydroxide, use our balanced equation to calculate moles of carbon dioxide, and then use the ideal gas law to calculate volume again. All right, so let's give it a try. Pause the video and see what kind of progress you can make before I go through it myself. All right, welcome back. I hope that you remember that when we are starting with volume, we're going to use our molarity to convert moles into, liters into moles. And now I'm using my balanced equation to convert moles of the lithium hydroxide into moles of CO2. And next, because I'm going to be using the ideal gas law, just as I did last time, I'm going to calculate moles and then use the ideal gas law separately. So my 2's conveniently canceled out here, so I end up with 5 moles of carbon dioxide. And so now my ideal gas law, I'm solving for volume again. And I just did the same typo I did last time. So we have 5 moles, 0.083145 liter bar per mole Kelvin, 298 Kelvin, and 1 bar. So the volume that I calculated was 1.79 times 10 to the 4 liters. So in other words, we have a pretty decent amount of gas that we can go through because this would be pure carbon dioxide, right? All right, so let's go ahead and try another practice problem just to see another different form. And this time I promise we won't calculate volume. So if we burn 235 grams of methane in excess oxygen and collect all of the carbon dioxide, we're going to collect it in a 10-liter tank at 298 Kelvin. And we will ask, what is the pressure of the tank? So why don't you see if you can solve this problem, and then I'll walk through it for you. Okay. The first thing that we need is a balanced equation. So I hope that you recognize that this was a combustion reaction, and so we should make carbon dioxide and water. And I have a fairly simple ratio here for our stoichiometry. So our next step is to identify A and B. I can see that I know about my methane, so that must be my A. And then I am asking about my carbon dioxide, so that must be my B. So I'm going from grams of A, and I want the pressure of B. So that would be 235 grams of methane that I need to convert into moles using the molecular weight. So my molecular weight I calculated to be 16.04 grams per mole. And I have a 1-to-1 mole relationship in this reaction. So I get 14.6 moles of carbon dioxide. And now this time, from my ideal gas law, I'm going to solve for the pressure. And you can choose which pressure unit you would like to go with. This time we'll go with atmospheres. Right, and our volume was 10 liters. So if we plug in all those numbers, I got 35.8 atmospheres. Okay, so hopefully these calculations are feeling pretty comfortable. And if you do have any questions about doing any of these calculations, please make sure you just let me know.